Well, hi everyone, Dr. J here, and in this video we're going to be talking about structure from motion. And I will introduce the topic for us and talk about its application in UAV systems. So structure from motion is basically a technique that's used to take 2D photographs with 2D information on them and to develop 3D models and orthorectified mosaics. In other words, get true 3D information and get information that can be used for making actual measurements. So we're going to take 2D photographs and we're going to extract basically full 3D information. So I've got here just an example of a bunch of images, and we're going to use information in those images and tie those things together in order to extract real 3D locations in the real world. Now, just the images by themselves won't be able to give us that. We'll need some additional information about either ground control points or maybe GPS coordinates of camera positions, something like that. But we'll be able to, given that information, take 2D images and turn it into 3D information. And that includes both orthomosaics, so orthorectified and georeferenced mosaics, photomosaics, as well as actual 3D models where we can actually get 3D point clouds and digital surface models and things like that. This involves several steps, so there's going to be some point matching involved, some camera calibration and parameter estimation. There's going to be the DEM generation itself, which leads to a 3D model, and that will essentially be our final product. We can sort of have different classes of these. There's aerial versus terrestrial, so we're going to be talking in this class primarily about aerial photography from drones, but you can also do this from just regular cameras. You can do it from satellite cameras. So there's lots of different applications of photogrammetry. And you can also have two kinds of missions. One which is capturing primarily vertical photographs or near vertical photographs, and then a different mission which is capturing more oblique imagery. And there's going to be some different use cases where these are more used more often. So let's just review the geometry of imaging, and we're going to kind of use the vertical imaging geometry to start out with. So we've got our camera lens here, and this is going to work the same way as our eyes work. So it focuses light at a particular point, which is the lens, and then the lens is going to allow light to pass through and focus it onto a focal plane. And this distance between the lens and the focal plane is the focal length, and we'll call that F normally. There's going to be a height above the ground, the height of the lens above the ground, and then there's going to be an additional height above a datum, which in this case I'm showing it as sea level, but it could be an ellipsoid or something like that. We're going to say that the scale of the image scale, is the image distance, which is essentially the distance across the image focal plane, divided by the object distance. So this ratio here, and you can see these are going to be similar triangles, and so the image distance here over the object distance, that's going to be the scale of the image. And you can see also that the scale is going to depend on the height. And so actually, if your height changes, goes up or down, then the object distance is going to change as a result of that. The image distance won't change. That's going to be fixed in most cases. And so then your scale will change. So you can get a larger scale map by flying higher, or you can get a more detailed map by flying lower. Here's just another image of that, or another cartoon schematic of that same kind of thing. We've got our image plane here. Now our image plane is actually in front of the focal point, or the perspective center, as we'll call it. There's our focal length there. Here's again our height above the ground. Here's our datum height, capital H. And terrain and datum is there. And we can also express our scale as the ratio between the focal length and the elevation above the ground. Now here's our focal length here. And again, this works because of these being similar triangles. So here you can see it's pretty easy because we have a positive image plane. And so you can pretty clearly see that this triangle here is going to be similar to this triangle here. And so then this distance here is going to be the same as this distance here, or not the same as, but these distances will correspond, and they'll correspond in the same way that this distance, the image plane distance, corresponds to the object plane distance. And so that scale can also be expressed as a ratio of those numbers. Now, in reality, our scales are not exactly, they're not constant for a particular photograph. Now, if you have a pure vertical photograph, it'll be fairly constant across the photograph, as shown here. But in reality, there's almost always some degree of non-verticalness in the photograph. And also, because we have this perspective, there's going to be this distortion of points on the ground or points in your image, and that distortion is going to depend on the location in the photograph. And so actually there can be different scales, and there are different scales in the direction that's in the look, that would be in the direction away, pointing away from the camera, and in the direction transverse to that direction. So you can actually see here the scale is different in this direction than it is in this direction. There's more distortion in this direction. So here's an example question for us about scale and focal length. We've got a vertical photograph taken at 800 meters above sea level. The terrain is flat at an elevation of 237 meters above sea level. What is the scale of the image if the camera has a focal length of 50 millimeters? So we can go back to our equation here. Here's our focal length, here's our height above the ground. We can just take that ratio and get the scale of the image. So we've got our focal length of 0.05 meters, that's 50 millimeters. And then our elevation is 800 meters above sea level, and we're going to subtract out the elevation of the ground. And so the ground is at 237. 800 minus 237 is 563 meters. That's our height that our camera is above the ground. And so we take 50 millimeters, which is 0.05 meters, divide that by 563 meters, and we kind of, you get a number which we'll round into a ratio, and that ratio is going to be 1 to 11,260. Now, as I mentioned, the scale changes as a function of direction. And so here's a case where we have an oblique photograph taken that includes a road intersection. And you see the roads here they do not look like they're the same width, but they actually are both 10 meters wide. And so this is happening because of this direction-dependent scale factor. So in the image, A is 5 millimeters, that's the distance across this road in the image, and B is 2 millimeters. What are the photo scales along those directions? What are the photo scales along direction A and direction B? Well, we do the same thing. We've got 5 millimeters, and we're going to divide that by 10 meters of the actual distance. And so 0.05 meters divided by 10 meters, that's going to be a scale of 1 to 2,000. So that'll be this scale. And then for B is a different number. So B is 2 millimeters in the image for 10 meters in reality. And so that's going to give us a 1 to 5,000 ratio. Okay, so the scale can change depending on the direction. This is an example, or this different scales and different directions also leads to something called relief displacement, where if we're looking at the center of a photograph, we can look straight down in a vertical photograph, and objects in the center will appear to be viewed from straight above. But objects off to the side are going to appear to be leaning away from the center. So you see how this top and this bottom objects appear to be leaning away from the center, and the same thing as you sort of go along these axes. So here it's leaning directly away from the center. Whoops. It's leaning directly away. Here it's leaning at it. So here these objects are all leaning in the axes, so there's no distortion in the vertical axis, but there's distortion in the horizontal. Here there's no distortion in the horizontal, but there's distortion in the vertical. And then of course in the off in the diagonals, there's distortion in both horizontal and vertical direction. So this is the result of the perspective view. And this is what we're going to leverage. We're actually going to leverage this information to estimate things like the height of those objects. So this relief displacement is what we'll use, and you can see here's an image plane at the top, and we're looking at images, and you can see that this distortion, this relief displacement, is a result of the fact that the line connecting the perspective center, or the focal point, is not the same for the top of the object on the ground and the bottom. There's a slight difference there. And so that slight difference is what results in this relief displacement. We can put some numbers. Numbers, or maybe I should say letters. We can assign some variables to these different things. So the height of the object, we'll call that h. The height of the object above the datum, we'll call hb. That's the elevation, basically, of the base of the object. We've got the height of the camera above the ground, that's h prime, and the height of the camera above the datum, that's h. And then we've also got RB and RT, that's the image distance. So now this is the image, this is the real object, this is the image of the object. We have a distance from the origin in the photograph of the base of the object and the top of the object. And there you see that relief displacement of the top because of the different imaging geometries that you have here. And I'll just put some more definitions up on the slide for you. So here's the projection. Here's the image plane. This is, of course, the image itself. The projection of the object onto the image plane is, you can see where that will happen with these blue lines that trace from the perspective center to the object. And that corresponds to this part of the image here. So here's the object as it's seen in the image. It's the projection of the object onto the image. We'll also define D here, and I don't have D marked. D is the distance from the perspective center of the camera to the base of the object in the real world space. So it's the distance from this dashed line here to the base of the object itself. This distance is our D distance. And here's just another schematic diagram showing this distance and also showing some relationships between these parameters. So we can take the ratio of this distance here. This is the distance in the image from the origin of the photo to the base of the object. Capital D is the distance in the real world from the perspective center of the camera to the base of the object. Well, just the distance to the object. So this D here, here's our camera focal point or perspective center. Here's our focal plane. This line here is our focal plane. Here RB is that distance in the focal plane. It's this distance here in the image from the origin of the image to the base of the object. There's that line going from the perspective center to the base of the object. And so that's the projection of that base right there. Whoops, back up again. And then here's the line going from the perspective center or focal point through the image plane. So there's that point on the image plane, RT, to the top of the image in the real world space. And then this distance here, and again, we're using similar triangles for these relationships. So this triangle that's formed with this line is going to be the same as this triangle here from the base of the image all the way up there. So think about this in terms of this triangle here and then this triangle here. We've also got another triangle which is from to the top of the object. So there's that triangle, and that's the same as this triangle here. When I say the same, I mean similar. These are similar triangles. They share angles and sides, and so you can express the sides and angles. You can express the sides as ratios of each other, of these similar triangles. And so we have here RB over D. RB is this side of this triangle. D is going to be this distance here. That ratio is also equal to F over H. So F is the focal length of the camera. This length here, that's going to be proportional with this height, the height above the datum. And in this case, I guess we've sort of simplified things. So the height above the datum is also the height of the base of the object, but you could do that correction for if you had a elevation above the datum. So in this diagram, the datum and the object base are at the same height. Okay, so this distance here, the ratio of this distance to this D distance is the same. It equals this focal height, that height divided by the total height above the datum. And so we can rearrange that expression to give us this. D now is the distance from the camera to the object, and that's given by this expression, H times RB times F. So think about this now. F comes from the camera, that's the focal length. Whoops. So think about this now. F comes from the camera, that's the focal length. RB comes from the image. We can just get that by looking at the image. And then if we know what height we're flying, we can calculate the distance d. Similarly, we can do a similar kind of thing with these ratios. Here's our t, that's our distance here along the image plane. And again, this image here is this image plane here. So this is the image plane that corresponds to this particular image. So our t is the distance here along the image plane to the line going through to the top of the object. There's that there. And then that is going to be related to d. The ratio of that to d, again, is going to be equal to the ratio of the focal length to not h, but now h minus little h, which is h, little h here is the height of the object. So little h is the height of the object. We subtract that from our overall height. So that is this height. That's this distance here. And you should be able to see from similar triangles that the ratio of this length to, the ratio of this length to this length is the same as the ratio of this height to this height. So that's what we're getting from similar triangles there. And so both of these can be rearranged to solve for d, and then we can set these equal to each other. And so we can set both of them, use both of these expressions here on the right-hand side, which are equal to d. We can set those equal to each other, and then we can rearrange here and solve for the displacement, the relief displacement here on the left, which is a function of the distance to the top of the object in the image plane, and then multiply by a ratio of the object height to the height of the camera above the base of the object. And so with this now, we can calculate what that relief displacement would be, or we can rearrange this equation to now be a relationship between delta r, which is the relief displacement that we measure in the image, over RT, which is that distance to the top of the image, top of the object in the image. So there's those two numbers there. H prime, which is the height of the camera above the base of the object. If we know those three things, we can actually calculate what is H, what is the height of the object itself. And so this is really cool. We can take just information about where the camera was located and what we can already measure because we have the picture, and we can calculate what the actual height of the object was using this ratio. So what did we do? We took similar triangles and just the imaging geometry. We calculated what this distance was in two different ways, using these parameters and the height of the object. Then we said, well, we can rearrange this both to solve for that d parameter, that distance parameter, set these two equal to each other, and then just simplify down. There's our relief displacement, there's our RT distance. Here is our initial photogrammetry result. We can solve for the height of an object in an image just by knowing things about the camera, how high it was above the ground, and things from the image itself. What is this relief displacement? And what is the distance from the top to the top of that object from the origin point of our photograph? So let's do an example. A photograph is taken with a 155mm focal length camera. Two objects in the photo are 32mm apart. In the photo, the actual elevations of those 2 points are 700 feet, and the actual distance between those 2 points is 455 feet. How high is the camera flying? Now, this is kind of interesting because we didn't talk about this, but we can actually see just by going back here, if we know these pieces of information, if we know any three of these pieces of information, we can solve for the other one. So in this case, we don't know the camera height. We want to solve for the camera height. Maybe in this case, this is your ground control points. So you've made measurements of ground control points, and now you know where those are located. You know where your ground control is located, you know their elevations, and you want to know the exact position of your camera. So here we're going to use the fact that the image distance over the ground distance is equal to the scale, and that's also related to the focal length. So we have 32mm is our image distance, and that's going to be divided by 455 feet. So 455 feet is the actual ground distance between those two objects, and 32mm is the image distance. That is our image scale. But we can also say that our image scale is also equal to f over h minus h, right? That was what we had talked about before. And so that's going to equal 155mm divided by the the height of the actual elevations of those points, which is h, that's the height of our camera that we're trying to solve for, minus 700 feet. Minus 700 feet. So we can, here's our elevation of our ground, here's our elevation of our camera above our datum, there's our focal length, and there's our image distance to ground distance. So we can take this ratio and this ratio, we can rearrange this and solve for what h would be. How do we do the rearrangement? Well, we cross multiply, we take this, put it up here, take 32, put it down there, and that gives us h minus 700 divided by 455. Now our units cancel out, so that's good. We've got feet over feet. This is 700 feet, by the way. And that's going to equal 155 over 32. And again, these are both in millimeters, so the millimeters cancels out. We can take now this number, 155 divided by 32, that's about 4.8. 4.84. We can take 4.84, multiply it by 455, and then we need to add 700, and that will give us our camera elevation, and that's approximately h equals to 2,900 feet. It's actually about 2,902 or so, but roughly 2,900 feet. So there we were able to work out our camera height just by knowing information about the image, 32 millimeters apart in the image. We know the actual elevations of those points, so these would be like our ground control points, and we know our camera focal length. All right, let's do one more example. We've got here an example where we've got a photograph, and in that photograph we have a building which exhibits relief displacement of 5 millimeters, and its top is located 45 millimeters from the perspective center. The photograph was taken from an elevation of 3,200 feet AGL, above ground level. What is the elevation of the top of the building? So first of all, notice that we've got above ground level elevation, and so we don't need to do the correction for above the datum. We've already done that correction in this number. So very simply, the elevation of the top of the building is going to be our actually delta R measurement. So our relief displacement divided by that RT times our h prime, that's the height of the camera above the ground, or above the base of the object. That's going to be, in this case, 5 millimeters. And we'll divide that by 45 millimeters. And then we're going to multiply that whole thing by 3,200. 3,200 feet. And so our units will also be of our solution. Millimeters over millimeters will cancel out, and so we'll end up with units of feet, which is what we want for our height of our building. And let's see, so 5 divided by 45, that's about 0.11. And then we're going to multiply that by 3,200, and that's going to give us our height in feet, and that number is going to be about 355 feet. And there's some decimals there, but I'm not going to worry about those. So our building height is roughly 355 feet based on a camera or a photograph taken from an elevation of 3,200 feet AGL, a relief displacement of 5 millimeters, and a distance from the perspective center to the top of the building of 45 millimeters. All right. So that's going to do it for this video. In the next video, we'll talk a little bit more in more detail about stereo vision and parallax and how those things can help us in the photogrammetric process.